Merhaba arkadaşlar. Mikro işlemci dersine, mikroprosesör dersine hoş geldiniz. Biz bu dersi, laboratuvar dersini de sağ olsun Abbas hocamızla beraber devam edeceğiz. Uzun yıllardır, uzun zamandır zaten asiste ediyormuş. Normalde herhalde Mustafa Oral hocamız veriyordu. Benim de
Evet hocam.
Mustafa Oral hocamız benim de yüksek lisanstan hocamdır. Çok kıymetli bir hocamdır. Çok sever ve saygı duyarım.
Maşallah.
Aynen sağ olsun. Şimdi bu artık bize rica ettiler. Abbas hocam da sağ olsun bizi kırmadı. Bu laboratuvar derslerini beraber yürüteceğiz. Ben burada sözü Abbas hocama bırakmak istiyorum. Yine bana düşen bir şey olursa ben gerekli yapmam gerekenleri yapacağım. Evet, kolaylıklar dilerim hocam. Abbas hocam çok teşekkür ederim.
Ben teşekkür ederim hocam. Sağ olun. Bu
Ben
girdiler.
dinlemedeyim, kayıttayım hocam.
Sağ olun hocam. Teşekkür
Sağ olun.
ederiz.
Sağ olun. Sağ olun.
Arkadaşlar merhaba. Geçen haftaki derse katılanlar biliyordur. Bir dersi nasıl işleyeceğiz, hangi emülatörü kullanacağız, duyuruları nereden yapacağız şeklinde bir girizgah yapmıştım. Şimdi katılımcıların biraz daha artmasını bekliyorum. Bu ilk dersler diğerlerine nazaran daha önemli dersler. Sonrasında da İngilizceye geçip derse başlayacağım. Şimdi hatırlarsanız ne demiştik? AABBS.tr diye bir sitem var demiştim. Burada lecturing altında Microprocessor Lab kısmında tüm duyurularımız, dosyalarımız, emülatörümüz bu download butonunun altında duruyor arkadaşlar. Küçük bir dosya zaten 2.85 MB gibi bir şey. İndirip yükleyecektiniz. Umarım yüklemişsinizdir çünkü kurcalamanızı istiyorum. Bol bol kurcalamanızı istiyorum. Bu derse giren, bu emülatörü kurcalayan bu dersi geçer. Bu kadar basit aslında. Çünkü C'yi öğrendiniz ve geçtiyseniz assembly çok da zor değil. Başta karmaşık geliyor sadece. Onun dışında arkadaşlar şöyle deney föylerimiz, eski adı deney föylerimiz ama lab assignment olarak geçen PDF'lerimiz var. Yine aynı sitede 1, 2, 3, 4, 5, 6 lab olarak geçen PDF'lerimiz var. Mesela birazdan bu Lab Assignment 1'i işleyeceğiz. İşte içerisinde komutlarımız var. Bu komutların ne yaptığını anlatan küçük description'larımız var. En sonunda da ikinci sayfada bir örnekler var. Examples olarak geçen 3 soru var. Normalde pandemi olmasaydı bölümümüzde, laboratuvarımızda işleyecektik bu dersi. Ben yukarıdaki kod, instruction setleri anlattıktan sonra sizlerden soruları açıklayıp her bir soruyu çözmeniz için zaman vereceğim. Sizin çözmenizi bekleyecektim. Ama pandemiden dolayı online işlediğimizden ben çözeceğim. Tek tek yavaş yavaş anlatarak. Lab dersimiz assembly dilini öğrenme dersi gibi olacak sizler için. PDF'imiz buydu. Emülatörümüzü hatırlayalım. Emülatörümüz şöyle 8086 simgeli bir yeşil simgeli emülatörümüz 4.8 diyorduk. Help butonumuz vardı. Bizim için önemli olan. Bunu hatırlayalım. Help butonumuzda çeşitli tutorial'lar altında başka tutorial'lar vardı ama bizim için en önemli kısım 8086 instruction set dediğimiz şu üstteki kısımda arkadaşlar. Burada bu dönem boyunca işleyeceğimiz instruction'lar var. Aşağı doğru zaten başlıyorlar. Tek sayfa burası. İşte mesela bugünün ilk konusu move komutu. Move komutu nedir ne değildir? Bu help dosyasını okumayı anlatmıştık. İşte birinci sütunda komut, ikinci sütunda parametreleri, birinci parametre, ikinci parametre, alabildiği parametre tipleri satır satır. Mesela register memory alabiliyormuş, memory register alabiliyormuş gibi 2 parametre alıyor. İşte burada ne iş yaptığı şey olarak İngilizce açıklama olarak. Burada varsa bir açıklama kısmı, algoritması, örnek kodu, etkilediği bayraklar şeklinde bir açıklama yapmıştık. Şimdi müsaadenizle 15 kişi katılım var. Katılan arkadaşlara sesleniyorum arkadaşlar. Gerçekten bu dersi dinlemek çok önemli. Çünkü online sınav yapacağız büyük ihtimalle. Emülatörünüz açık olacak. Bu emülatörü kullanmayı bilmezseniz çok basit soruları yapamazsınız. Ben de sürekli bu emülatörü kullanacağım için derslere katılmaya çalışın. Katılamasanız bile izlemeye çalışın. Katılmaya çalışın diye ısrar etmemin sebebi, mesela sabahki grupta çeşitli sorular vardı. Dersin sonunda soruları aldım. Bir 15-20 dakikada soru cevapladık. Anlamadıkları yerleri sordular. O şekilde gidersek daha iyi olur. Bir de bana bir şey söylemek isteyen, derste araya girmek isteyen olursa mikrofonunu açıp hocam diye araya girerse daha iyi olur. Çünkü ben bunu indirdiğim zaman bir şey göremiyorum. Sizler ne yazıyorsunuz, ne yapıyorsunuz. Dedikten sonra let's switch it into English. Okay, my friends. Today we are going to talk about the first assignment, which is 3 commands, 3 instruction set. Move instruction, add instruction, subtract instruction. Before diving into this lab assignment, I'm going to explain in detail some emulator functionalities. Let me start with some simple code. It's not important for now. I'm going to explain this code later. Okay, there are some codes I'm writing. I start with writing some numbers. These numbers are in different formats. Our emulator can support 3 types of number formats. One of them is binary format. If you want to use numbers as a binary, you can directly use 1001, whatever you want to use, but you have to put B at the end of this number. If you want to use hexadecimal number, which is the default working, how can I say, default working number system of this emulator, you have to put H at the end of number or value. If you want to work with decimal, the 10 base number system, you have to use D, decimal D. If you don't put anything, emulator automatically thinks that this is decimal. So be careful. If you don't put anything, it becomes decimal. H is for hexadecimal, B is for binary, and D is for also decimal. So these are same things with first line. Okay, these are the numbers. And for now, this is not the correct way of ending the, how can I say, program in assembly. This is just a function return or procedure return. This is not the correct way, but we are going to implement when the topic was interrupts. I'm going to show you the correct way of returning procedure to operating system interrupts. So far, just know that Reds just ends this functions or codes. Okay, when we emulate this code, remember, this is our written code, line by line, highlighting with yellow. And there is 2 columns. The left column is, remember, our memory, directly our memory. Every line of this memory block, as you can see with highlighted with yellow, is 1 byte, which is 8-bit. As you can see also, because for example, 1C address consists of C3, which is 8-bit. In hexadecimal, every character is 4-bit. Remember, FF or F. What is F in binary? F in binary is 1111. So 4-bit is 1 character in hexadecimal. So this is 2 character. 2 character means 8-bit. 8-bit means byte, 1 byte. So when you see any B in right part of this code, let me reload this one. Any B out there? No, there is no B because these are all AX. Move CL73 hash. Move 1000 H. It doesn't work that way. I'm trying to show you something, but it insists not use the B. Okay, I got the B. In here, the right part of this column, every B character you see means byte, 8-bit. If you see a word, for example, I'm going to put a word in some address, you see W. W means word. Word means 16-bit, 2 byte. These are all same thing. But you have to know this. 16-bit, 2 byte, word. These are all same thing in 8086 architecture. By the way, it depends. Byte is all same in every architecture, but it depends. Some architecture change these words into 32-bit or even 46-bit. So in 8086, it is 16-bit as a word. Okay, now that I mentioned that, we have two columns. Every line is 8-bit. The right part is assembly code. The machine code we have seen. This is our written code, highlighted with current line. You can go step by single step. Run your code with single step and forward and backward. Generally, debug development environment doesn't support the step back option, but this emulator supports back option. You can turn back at reload, by the way. It starts from the beginning. There is a little break. You can run your code and see it with a little delay. We are not going to use delay for now. The left part is registers. Let me zoom in this left part. Registers. Registers are important part of this lesson. We keep using the registers. There are 4 16-bit registers. There are 8 8-bit registers. These are all 8-bit registers. So beware. AX, BX, DX, DX. These are 16-bit registers. Consist of lower boundary and higher boundaries of itself. These are 16-bit ones, and these are 8-bit and 8-bit. This goes like that. But you have to be careful. For example, I'm going to, let's see that after this lesson, because I'm going to use move command and it can be complicated. Registers. You can't define a variable for now. After some time, we cover that topic in a different way. But for now, know that there is no variable. You have to use previously defined registers, which is A, B, C, D. Segments. Segments are important. I call them twins. I couldn't remember the correct phrase for these twins, but let me show the segments again. There are code segments, text segments, data segments, and exa segments. Segments means a pointer. Actually it's a register, but it stores the pointer of a data. For example, code segments showing where the written code, the machine code, has stored in the memory. When you write a code, for example, let's write a simple code. Move AX 73, increase AX, decrease BX, red. This is just a simple code. This code has 3 lines with red, it's 4. It stores in the memory. When you run this code, emulate this code is copied into memory. The memory location of this code is shown by code segment instruction pointer twins. Code segment instruction pointer twin, which is 100 and 000, shows us the location of these instructions. These instructions are now at memory. It's stored where code segment instruction pointer combination. For example, I'm going to go single step forward. When I go single step forward, let's look at the instruction pointer. Instruction pointer becomes blue. Blue means that value is changed. Instruction pointer have always changed because it shows the next instruction, which is going to be run. Okay, so instruction point is showing that 3, which means code segment instruction pointer combination of physical address, which is 1003, will be the next instruction this code is going to run. So code segment instruction pointer is a twin. We are not going to change code segment because it doesn't necessary. It just loads the code into default value. But we are going to change the other segments because, for example, data segment is 100 also. If you are going to use data segments with code segment the same place, things may corrupt because this is also code, this is also value, so it may conflict with instruction. That's why we are going to change the data segment, not the code segment, but data segment, because we keep working on data segment. Okay, this is twin, code segment instruction pointer. By the way, you can change instruction pointer in any way. It just changes, it updates itself. So you just watch it. Okay, let's erase these twins and comes to stack segment. Stack segment has a twin also, which is stack pointer. Stack pointer is a twin. It shows where the current stack pointer head is storing. When you put when you click the stack buttons, this is our stack, the head of the stack, and while decreasing, it shows the head of the stack. It is 100 and FFFE. As you can see, head of the stack is 100 and FFFE. So stack segment stack pointer is showing our stack, where is stack is stored. So this is another twin. Let's get rid of them for now. Data segment and exa segment. These two is our most important segments. We keep working on these two. Actually, most of the lessons will go over from data segment, but after some time, we are going to use exa segment to move objects, move part of the object memory. So I'm going to I'm going to delete, but let's write these twins. Data segment, source index, exa segment, destination index. Data segment, source index. Yeah, exa segment, destination index. These are twins. You have to memorize these twins. We keep using these twin combinations. Don't forget. Data segment, source index, exa segment, destination index. Okay, we are going to cover the exa segment later. I delete that. So, data segment, source index. When we open the new document, remember we use empty workspace. Empty workspace comes with default segments. What is the default value? Default value is 100H hexadecimal. Bakın, code segment, stack segment, exa segment, destination segment. All is 100H. So 100H semicolon What is the source index? Source index is 0, 0, 0, 0. This is the default value. As you can see, the address is here. While debugging our code, there is no screens like showing the variable value from somewhere. We keep using this left column, enter some value in here, and look at the memory location and its context. That's why we have to know the calculation of physical address. What is physical address? This is address. Calculation of this location to physical location of this address is, for example, 1050. How we are going to calculate this? Let's go over this example. For example, segment value. The first part of this address is segment value. It doesn't matter, it's just segment. 0, 100H. The right part 0050H, 0050H. All of these values are hexadecimal. While calculating, this is segment part. This is the right part. I couldn't remember the name again. Calculation of the physical address is like adding a 0 at the end of a segment. This is important. Adding a 0 at the end of a segment. We put 0 at the end of a segment and add this together. What is the value? It is 01050H. The physical address of this data segment address combination, this address combination physical address is 01050, which is, as you can see in here. If you update your code and enter, it goes to that physical address. For example, segment value is 100. We put 0 at the end of segment value, which becomes 1000, and there is no other value at the right part. The physical address is 1000. I'm going to ask a simple question now. 200, 200. What will be the physical address of this address? I want you to answer this question, please. What will be the physical address of this 200 and 200H? That is what we have learned. Is there anybody who can answer my question? 2000 and 200, said Mohammed. Yeah, it is H, exactly that. So it is 200 and 200. We put 0 at the end of segment and add this together. It becomes 2200H. When I enter this in here, you can see the physical address of this address. Okay, now we learn how to calculate the physical address. Now we can dive into our lab assignment now. Okay, move command. Move command has two parameters. First parameter is destination operand. Second parameter is source operand. It may confuse your mind. It's just a operation of copying second operand to first operand. Remember, when we learn a new command, we open help, go to instruction set, and look at that command. What is saying? Copy operand 2 to operand 1. Description copies the second operand to the first operand. The source operand can be an immediate value, general, blah, blah, blah. Both operands must be same size, which can be byte, word, double word, etc. Description is not very good. That's why I'm going to show you the probabilities, usage probabilities of this move command. For example, move. We are going to use first operand. like in here, register memory combination. What is register? Register, for example, AX. Memory, what is memory? It's called like this. 1000H address of that location. Address of 1000H. It gathers the value from 1000H. They are completely different things. Please don't confuse these two. Let me first put some value in 1000H. 73 hash. And show you the example what it is doing. Just never mind the first line. Okay. 1000H address. It goes to 1000H address. Let's go to 1000H. Its physical location is 2000 because code segment is data segment is 100. 100 to plus 1000 is 2000. 73 is at 2000 physical location. But on the second line, when we run this code, as you can see, the AL is updated. Actually, AX is updated, but A hash is not changed, so only AL is updated. We put, it didn't run yet. Let's run it, yep. We update the AX with 1000H value. So these two things is very different. Just remember, this gathers the value from that memory. This is just a value. We put those values into AX. These are different things. So let's go over and come here. This is the register memory combination. Let's write the exactly opposite one. Memory register combination. Register combination. Memory immediate. Immediate means value. This is just a number, just a value to put. We put 1000H into 1000H address. Did you catch that? So this is immediate to memory. And there's another immediate to register, for example, CX273. This is immediate to register. And other ones, S register. S register means segment register. Segment register also can be updated with move command. For example, data segment. Data segment can be updated with memory. Also, the value that data segment stores can be learned by calling move function. By this line, we can learn where is data segment, where data segment is showing. And another one, move data segment value into AX, and the most we are going to use one into register value into data segment. But the most and the how can I say, the easiest part the students can't catch. You can't directly update data segment. This is wrong usage. Let me when you emulate this, it gives you errors. Cannot use segment register with immediate value. Segment register doesn't have a combination with immediate value. So if you want to update data segment, you have to use another variable beforehand. For example, let's update data segment with AX. I'm going to update data segment as 200H and move AX into DS. Yeah, that's it. Put 200 into AX. As you can see, AX is now 200H. Update the data segment. As you can see, data segment is now 200. Okay, changing data segment is this way. You can also use memory too. For example, value into some memory and gather that memory into data segment. Okay, and you emulate this code and run this one. Let's go over and look at the 1000H. 1000H has 200. 200 is not fit into 8-bit, so it overflow into next byte, which is 2001. When you copy this 1000H into data segment, it copies a word because data segment is 16-bit. It gathers a word 16-bit from the memory, and when you run this, you can see data segment is also updated. This is another way to change, but we mostly use the previous one, which is this. It doesn't have to be AX. It can be B, C, D. We have 4 registers. By the way, these registers names comes from the accumulator register, AX, base register, BX, counter register, CX, and D. What was D for? I couldn't remember the D. D has also some name, but I couldn't remember it. I'm going to find it. Not memory access. Variables. Not variables. Assembly language. Yeah, data register. That's simple. DX is data register. Yeah. As you can see, our help is helpful, even for me. Okay, use it. So move function. Move function is this. Let's go over and look at the second instruction, add instruction. What we are going to do, it's a new instruction. I'm going to learn this. I open help, go to instruction set, and open the add command. Add command is here. The first line is comment. First column is comment. Second column is the parameter types it can get. Algorithm. Algorithm is just add. It just adds. But what is the algorithm? Adding operand 1 and operand 2 into operand 1. As you can see, operand 1 equals to operand 1 plus operand 2. This is algorithmic showing. And there's an example code. Let's run this example code. Okay. By the way, you can directly use -3 like this. You can use -3. You don't have to use FFFE or something. You can use -3 directly. When you emulate this, it already converts -3 into FD. FD is -3. How can we know that? We have a converter. When you go and write -3, it says 8-bit -3 is FD. 16-bit -3 is FFFD. Remember, size is important because sign bit must be the first one. So that's why it keeps adding 1 at the beginning. Anyway, this is -3. So what it's doing, it puts 5 into AL. Okay, AL is 5. What is the operation? Operation is, let me open this. Add operation. Adding AL plus -3 equals to AL. So 5 plus -3 is 2. It will store into AL. Okay, when we run this, look at here, AL is 2. 5 minus 3 is 2. This is add operation, but this example is a bit meaningless. Five and 3, we put 5 and add and store the value in AL. We can use another variable, for example, BL, 3, and use AL plus BL, and result will be also AL2, AL5, BL3, result is 8. Remember, the AL and AH, the upper bound of higher bound of A is and lower bound of A is different registers. When you use 8-bit register, so I can use AH. For example, this is also correct usage. Result will be in AL2. 5 is in the lower part, 3 in the high part, the result 8 in the lower part. That's it. Add operation. What are the types it can get? It can be register memory, add register memory, memory register, vice versa, register, memory immediate, this is important, memory immediate, it adds the 73 decimal into a value what 1000H address stores and add the 2 number and stores that value into 1000H again. For example, let's make a simple example. Move 1000H 5, the previous example, and I'm going to add 3. Okay. Let's go over and look at the 1000H. It's storing 5 hexadecimal. We didn't put H, but decimal 5 and hexadecimal 5 are same. That's why it's hexadecimal 5. Okay. So we add operation. We add 3 into 5 and store this value into 1000 again. And go over and look at the 1000. 1000H is 8. This is another type of add. Memory immediate, and the last one, register immediate. What's that? Not move, add register immediate. This is the most used one actually, adding some value into register. Register immediate. Okay, that's it. Third instruction, subtract, çıkarma. I open the instruction set, go to subtract command. The left part, the left column is command, parameters, explain, explanation, algorithm, example, goes like that. What is the explanation? It's subtract algorithm. It subtracts operand 1 from operand 2. Operand 1 minus operand 2 will be stored into operand 1. A simple example. What it is doing, it moves 5 into AL, subtract 1 from AL, which is 5. 5 minus 1, which is equal to 4. 4 will be stored into AL. As you can see, AL is 4. This is subtract. Add and sub has same parameters. These are all same. That's why I'm not going to cover all one by one. And instructions are done. We get rid of this Chrome. Okay. There's important warning here. The sub instruction performs integer subtraction. It evaluates the result for both signed and unsigned integer operands and says to blah blah. These are not important. It's saying that, let's go over to sub and show the meaningful part of it. It's saying that it can change all the flags according to operation. For example, it's not example, but just done it. For example, if you subtract 5 minus 6, it becomes -1. And I'm going to open the flags for you. This is a bit advanced part. When you done this, sign flag means result is negative. So it's 1. It's saying that. Okay. Now the examples. We have 3 examples. Actually, these are very simple examples. That's why I'm just going to write them directly. What it is saying, it says write an Intel 8086 assembly code that will write 34H value to 1000H address and 2000H memory address. What are the physical locations of these both address? For example, this is 3000, this is 2000. How did I calculate it? You don't have to calculate. Just go over and write these addresses and see the physical address. This is 2000. And when you write 2 in here, it becomes 3000. Okay. These are the locations. We are going to copy 34. What is the copy operation? Copy operation is move. Move 1000H address to immediate value, which is 34. Move lower or bigger capital, it's not important. I'm just going to be consistent while writing. That's why I keep using capital letters. It's not important. 2000H, 34H, and return. That's it. We put values into 1000H and 2000H. When we go over and look at the 1000, it's 34. Go over and look at the 2000, it is 34, 3000. Physical address is 3000. Okay, but there is a little catch in here. It shows segment in here. The default value is 100. That's why I didn't change anything. It just goes and put the correct place. But let's say this is not 100. Let me change it into, for example, 300 and 300 again. Let's say this is our question. I have updated the question. I need to update data segment. So beforehand, I need to update data segment. But remember, we can't directly update data segment like this. We have to use a temporary variable, temporary something. Let's use bx this time. Putting 300H into bx and updating data segment with bx. By this way, we updated the position of 300 and 1000. What is the physical address of this? It is 4000, as you can see. Another catch is here. This is memory location. It automatically put a data segment at the beginning of it. This is the same thing. If you didn't write the previous prefix part of this data segment part, it puts data segment automatically. But when we are going to use with exe segment, you have to specifically write this prefix because it doesn't understand it is exa segment or data segment. It just puts data segment automatically. So that's why the correct code is like this. We have to put data segment in front of this memory addresses. Okay, not in parentheses, out of the parentheses, but as a prefix. Okay, that's it. The first question. Let's go over the second question. Write an Intel 8086 assembly code that will swap the values of CL and DL registers. We are going to swap the CL and DL register. It didn't state code segment, data segment, anything. So delete this code. We have a value in CL. Let's put some value in CL. I don't know, 11H. Move, what is DL? Some value into DL, which is 73H. And I'm going to swap this value in C. Remember, when you want to swap two registers, what you are going to do, you are going to define a new temporary variable, put the first variable into temporary, put second variable into first variable, put temporary variable into second variable. This is swap operation in 3 lines. We are going to do the same thing, but we didn't create a temporary variable, but previously defined ax, bx, gx, dx, whatever we are going to use. So I'm going to use, for example, ah as a temporary variable. At the beginning, I'm going to copy the CL into temporary variable. Put DL into CL. Okay, now CL and DL are same thing. DL and CL are same thing. Now I'm going to put back those temporary variable into DL. That's it. CL and DL. Let's say these are the values stored in the CL and DL, which are 11 and 73. We are going to use temporary variable as a AH. CL into AH, which is 11. Put DL into CL. DL is 73, CL is 11. We are going to update 11 is 73. Both of them is same. Now put those temporary variable back into DL. As we can see, CL and DL now swapped. That's it. Okay. These are 8-bit variables. 8-bit. All of them is 8-bit. Okay. The third question. The third question is write an Intel 8086 assembly code that will add 90H value written on 500H memory address with 52 value written on 501 memory address. Then write the result into 502. It's saying that in memory 500H there is a value which is 98H. In memory 501H, it's important, the value 52. Question wants you to add these two numbers and save the result into 502. So normally what you are going to do, you are going to call add function with 500H and 501H. We are going to store the result, which will be in 500H, into 502H. So this will be the first thing in my mind, but this is not the correct usage of add or move instruction, because let's go over and look at the add instruction. Add instruction doesn't have a memory to memory parameter. There is no memory to memory. So this gives errors. When you emulate this code, it says wrong parameters. There's something wrong. What is that? You can't directly add to memory. That's why we need to update this code. Update it what? We are going to get the 500 value from that memory location into register. Let me write it directly. For example, AL to 500H. And the second part is of BL, let's say BL 503H. Now make this add operation AL plus BL. Result will be stored into AL and put this AL into 502H. So this is the correct usage. What will be the result? 98 plus 52. I don't know. Let's calculate it. Open a calculator in program language mode. I don't know the name. You can use decimal, octal, binary, hexadecimal. From here, we are making hexadecimal addition operation. 98 plus 52 is EA, H, hexadecimal. So the result must be EA. Let's go over and run this code. I'm going to check if it is written in 500 and 501. It is 1500 because the data segment doesn't change. It is 100. We put 0 at the end of data segment. So it becomes 1000. 1000 plus 500 means 1500. Physical address is 1500. So 98 is here, 52 is here. We are going to copy these values from memory location into register. 98 into AL, 52 into BL. Now this add operation will be done and the result is EA. We are going to store this value into 502 and let's go over and look at the result. As you can see, 500, 501 and 502. The result is EA. Okay. There is another way of running this code. Add operation supports two register modes, but also register memory also supported. So let's not use this line. In order to comment out your code, you can use semicolon. Is it semicolon or semicolon? What I'm going to do, I'm going to directly use the 501H value here. Let's erase these lines. Okay, this is exactly the same thing. That value stored, 500 will be 98, 98 plus adding operation is here, 98, 52 plus 98 into AL, it will become EA, and it will be stored in 502. This is another way of adding operation. I know that add operation can support register to memory addition. Okay, this was the last question. From now, we can stop the recording here. Let me check with Okay, any question? I want to answer some question first. Burak, for now, know that you can't define new variable, okay? You can't for now. But later on, we are going to learn how to define new variable, but it's complicated. Okay. Any question? Muharrem Hocam,
Tekrar merhabalar. Arkadaşlar katılımınız için teşekkür ederim.
biz teşekkür ederiz
Kaydı
hocam.
durduruyorum şu anda. Var mı benden istediğiniz herhangi bir şey, sormak istediğiniz bir şey?
Başka soru olmadı hocam.
Tamam, teşekkürler. İyi akşamlar arkadaşlar. İyi akşamlar hocam.
İyi akşamlar Muharrem Hocam. Teşekkür ederiz.
Ben teşekkür ederim hocam.